So we're actually going to take a step back and dive a little deeper into the concept of the dot product. Alright, so I'm just going to take us through a quick example. I drew a little diagram here. We're going to dot 3, 4, and 1, 2. Very easy computation based on what we've learned before. It's really just 3 times 4, I'm sorry, 3 times 1. So I say it's really easy and then almost immediately screw it up. 3 times 1 plus 4 times 2. And as a result, we get 3 plus 8, which is a result of 11. And so we want to start thinking about, all right, well, what does that really give us? All right. And so what we're actually doing, and it's kind of a weird relationship, is, and there's a lot of different ways of explaining this, but when you talk about multiplying two expressions, algebraically, if it's something like in a polynomial sense, it's dependent on the number of terms. There's usually a distributive property involved in some capacity. So one thing that we could actually do, if I just kind of take the 3, 4 and the 1, 2 and kind of treat it like a product of binomials, from Algebra 1 or whatever the analog course was, we could use a little bit of FOIL, first, outer, inner, last, and say that this would amount to, because, the different ways in which we could multiply, because who's to say that it's just the corresponding parts. We could have the first multiplied, so 3 times 1, plus the outers multiplied, 3 times 2, the inners multiplied, 4 times 1, oops, put a little multiplication symbol there, I meant to put a plus sign, and then 4 times 2 to represent the last. So the big question that we would have here is, because when we did the dot product, we just took the 3 times the 1 and the 4 times the 2, and it ended up being a case of, well, how did we know to take those? How did we know not to include the outer and inner terms if we're thinking about it as a FOIL technique? All right, and so what the dot product does is it takes into account orientation. All right, so when we look at, and that's where this diagram comes into play. So if we look at the components that make up this diagram, all right, we have 1, 2. Oh, why did I make it 1, 3? Who knows? Oh, no, I did it correctly. I'm just questioning myself as always. So we have 1, 2. And then we have, let me just get a fresh new color here. Let me say green. So 3, 4. So 3, 4. All right, these lengths, and I'll just demonstrate it with a couple of them, correspond to those dimensions. All right, so just to prove, not prove, you know what I mean. So what we're doing when we're taking the dot product is we're taking the components that have the same orientation, aka the horizontal components, and multiplying them together, then adding to that the vertical components added together, multiplied together. So it's really the 1 times the 3 plus, I had a loss to where to put the plus here. You know what I'll do? Just smidge this down a little bit and put a big old plus right smack dab in the middle. And then the 2 times the 4. So we're looking at, as a result, you get your product of 3 plus your product plus your product of 8. All right, 2 times 4 gives you the 8, which gives you the result of 11. Right? But then we get into the idea of, okay, well, why that? what is that in fact telling you? For that, I actually have to go back to my early teachings in mathematics, and it's really kind of strange when you think about how things line up, or at least it's strange when I think about it, because maybe I'm just a strange guy, I don't know, but it seems like every time I'm teaching something, and maybe there's some subconscious design behind it, but every time I'm teaching something in one class, I'm teaching the origin story to it in another class. But sometimes it's even more extreme than that. Like, for example, in this case, my son, who's in currently in fifth grade, I just blanked there for a second. He is in fifth grade. Is learning about multiplication of fractions. All right, not just multiplication of fractions, but among other things. And so he's learning about it in context now. So it's not just a matter of saying, all right, what is 3 times 4? What is this times that? It is, what does it really, truly, and absolutely mean when you multiply 3 times 4? All right. So, like, the whole, if you remember back when you're learning about proportions for the first time, is over of equals percent over 100, you just memorize the rule maybe. And then later on, you kind of worried about, okay, well, why did that rule work the way it did? And in some cases, maybe you never did. You just know that is over of equals percent over 100. Well, now we're kind of at that point where we have to start thinking about things like that. So what is a 1 times a 3 telling us? It's telling us that we're applying a scale factor of 3 to the number 1. So we're tripling the number 1. The same idea holds true when you multiply a 2 by a 4, you're quadrupling the number 2. And so what we're getting as a result is a scalar multiple of each of the components of a vector that are determined based off of the components of another vector. All right, and so in effect, we're looking at a form of a dilation. And just the dilation is taking on a different form in the vertical component than it does for the horizontal component. All right. Now, what we do is we combine those two ideas. We get the scalar multiple in the horizontal direction, the scalar multiple in the vertical direction, and we add the two together, and now we have a quantity that represents the total upscale or downscale for the entire vector. All right. For one vector in the direction acting in the direction of the other. So what I did was I put the a couple of rules here just from Unit 1. One rule was the dot product, and it's not really a rule, it's just a notation A dot B. So we're dotting A and B. And so what we're looking at here is the amount of A acting in the direction of B. And because multiplication, whether it's a dot product or ordinary multiplication, the exception would be a cross product, but in most cases, multiplication is commutative. So if I wrote B dot A, I'm saying that it's the amount of B acting in the direction of A. All right, so it's giving us an upscale or a downscale. All right, versus the component, because we did talk about that back in the last unit. All right, apologies for the handwriting. And so what that actually gives us is, I'll just make a little arrow here, is the proportion of A acting in the direction of B. Right? So we're talking about, instead of it just being a raw quantity, we're talking about it being a fraction of whatever the magnitude of B is. Right? Now, I put the dot product notation A dot B over a 1 just to show that it actually really is the same thing when we talk about a dot product and the component of a vector acting in the direction of another vector. And it's just that we have that understood denominator of 1, right? So it's a proportion of A acting in the direction of B when we're talking about the component. But when we're talking about the dot, we can also kind of look at that as the proportion of A acting in the direction of B if B was a unit vector. Right? So the component allows for B to not necessarily be a unit vector. So you can actually kind of look at the component form as kind of a special case of the dot product or vice versa. Right? So either way would actually work. All right. So that's a kind of like a little brief history of the two ideas. Right? So whether it's a matter of doing it algebraically, getting more of a geometric sense, either way, it really just kind of drives at the idea that there is a true underlying meaning to all of this. So that brings us to the idea of a gradient. And what I did was I jotted down here one of the forms of the dot product rules. A dot B, U dot V is equal to the magnitudes multiplied by the cosine of the angle in between. And so what we were actually doing here is taking the gradient vector and dotting that against some vector u. All right, and specifically, we're assuming that that u is representing the unit vector. All right, so let me just kind of throw this in over here. So we would be looking at the magnitude of u, which would be 1, multiplied by the magnitude of the gradient vector. I'm just going to use a shorthand notation here. Multiplied by the cosine of the angle separating the two. All right, and so we're looking at 1 multiplied. So this whole thing is actually just going to end up simplifying down to the cosine. The magnitude of the gradient vector times the cosine of the angle, separating that and their respective unit vector. All right. So what we want to have is, when we think about tying this to the meaning of a dot product, because that was the whole idea behind it, is we would want to know the upscale associated with multiplying, using the dot product, the gradient vector by a unit vector. Right? So if we assume that, again, well, it's not really an assumption, it's just a fact, the unit vector has a magnitude of 1, so you multiply anything by 1, you're really just going to end up with whatever you started with. So what we're saying here is, as a result, we're talking about the gradient vector acting in the direction of the unit vector dependent on whatever the value is of that gradient vector, right? And so if there is no angle separating the two, then you get the full force of the gradient vector acting in the direction of the unit vector. If there is an angle separating the two, then you'd only get some component of that acting in the direction of the unit vector, right? And so that's where the theta comes into play, right? And so we talked about this as, if we want to have the gradient, because we distinguish it, and it's unfortunate, and I don't like it, but it's just become like the standard nomenclature, where we say the gradient vector to represent the vector valued function composed of the derivatives, the first order partials. Now, we could also look at that as a directional derivative, but we tend to think of a directional derivative as having a particular direction associated with it. If we're just looking at the first order partials in vector form, that would be the gradient vector. Now, if I want to have the largest possible magnitude of a gradient vector, then I would call that the gradient. All right, I don't like that, but that's the standard naming convention, if you will. All right. So the one thing that we talked about is that since the maximum value for cosine, oh, I wanted to go with a marker here. The maximum value for cosine is equal to 1. Any theta value that would allow cosine to be equal to 1 is going to give us the maximum gradient vector magnitude, which in turn is going to be the gradient. All right, so this is a little rehash of what we talked about in class like 2 videos ago. I've been kind of explaining this in different ways in the hopes that one of my explanations will stick. All right, that's the idea. All right, so looking at number 1, if I just want to find the gradient vector, that's simple. First order partial 2x with respect to x, with respect to y, 2y, gradient vector, almost wrote an x again. All right, that's not too bad. Now, if I want the magnitude of the gradient vector, all right, or the largest possible magnitude, what I'd be looking for is really this. Now, you could put a cosine of 0 on at the end if you want, but it's not going to amount to anything more substantial than that. All right, so we're looking at 4x squared plus 4y squared. Now, you can go ahead and simplify a little bit, but you're not going to really do much with this. I could pull out a 4 and root it. So 2 radical x squared plus y squared. But you can't do anything with the radical x squared plus y squared. Please, under no circumstances, make that an x plus y, because that is absolutely not true. All right, when in doubt, check it on Desmos or something, and just to make sure. But I can promise you that they are not equivalent. All right, so this would be your final answer. So what this tells me is that regardless of what x and y are, if I wanted to go in the path, in the direction of steepest ascent from whatever that point is, let's say it's 0, 0, then I would just plug in a 0, 0 into 2 radical x squared plus y squared, and that would give me the magnitude of the gradient vector, which is actually giving me a rate of change. It's giving me the slope. If you think of it in that context, because what we're talking about is slope moving in the x direction, but also moving in the y direction, and this combines the two ideas. All right, so it gives us, and when you really think about a dot product, it's telling us how much of the first order partial with respect to x is acting in the direction of the unit vector, and how much of the first order partial with respect to y is acting in the direction of the unit vector. All right, and then it's taking the sum total of that. So it's giving us the overall sense of the rate of change or the slope. All right. So, or in what we call the gradient, because it's projected into